In the next example, we have an expanding cube. The side lengths of this cube, the distance along the edges in any of the three directions, are all x. It's measured in meters now. So as that side length x increases, the cube expands. Now the question is, at what rate is the volume of the cube increasing when the side lengths x are 3 meters? So to answer that question, we need to first set up a volume function. So v of x is going to be the volume of the cube as a function of x. What's the volume of this cube? Well, in the side-to-side direction, it has length x. In the vertical direction, it has length x. So this square in front has area x. But now that area is moving front to back by a factor of x. So we multiply that area by yet another x. And thus the volume of the cube is x cubed. That's why we say cubed when we take something to the third power, precisely because cubing the side length gives us the volume of a cube. Alright, now we need to compute the derivative to find the rate of increase. So let's find the derivative of v. And to do that, I'm going to use the limit definition of the derivative. Remember, that's the instantaneous rate of change of the function v of x. That's measured by finding the average rate of change over some interval from x to x plus h, and then we take the limit as the length h of that interval goes to 0. Alright, so plugging in x plus h into the cubing function, we get x plus h cubed, and then we subtract off x cubed, divide by h, and take the limit. Very good. Now to evaluate this limit, we need to take x plus h to the third power. You might not be used to expanding something to the third power, so I encourage you to take out some scratch paper and check that this is indeed what it is. You can also think about these numbers 1, 3, 3, 1 that I'm writing down as coming from Pascal's triangle. Okay, so that right there, that's the formula you get if you expand x plus h cubed. On the other hand, we're subtracting off x cubed, so it looks like that. Now there's an x cubed out front, and we're subtracting off x cubed, so those two terms cancel. And now the limit as h goes to 0 of what left can be computed by, surprise, surprise, factoring out an h. Remember, you're always trying to factor a common factor of h from the numerator, because once you've done so, you can cancel that h with the h in the denominator. Now all that's left is that term on top, so taking the limit of that term on top, 3x squared plus 3xh plus h squared, we can just evaluate at h equals 0. That's a continuous function. So look at these two terms, they got h's. So that term is going to be going to 0, and that term is going to be going to 0. The only thing left is the 3x squared out front. So 3x squared is the derivative of x cubed. And it's also going to tell us the rate of expansion of the volume of our cube. Remember, we're supposed to find the rate of expansion at a particular x value, which was 3. So we should plug that into the derivative of the volume function. We get 3 times 3 squared. Well, that's 3 times 9, that's 27. So how do we interpret that answer? This tells us that the cube is adding 27 cubic meters, it's quite a lot of volume, per meter that the side length x increases. So that's the rate of increase of the volume when the side length is increased by a meter. The total volume increases by 27 meters cubed. But that depends depended on the particular value of 3. So I'd like to emphasize that this is the rate of expansion when the side length x is 3, right? Because we're not literally adding 1 meter and then measuring how much we increased. That is the instantaneous rate of change. That's the rate of expansion of the volume at the point x equals 3, when its side length is 3, when it's at that size. If we chose a different x value, we'd get a different rate of increase. For example, suppose that we had chosen 4 instead of 3. Then the derivative, plugging in 4 into the derivative, we're going to get a different number. We're getting 4 squared, which is 16, times 3. Well, that's 48. So it's a larger rate of expansion. When the side length x is 4, the cube is adding more volume. The cube is adding 48 meters cubed of volume for every unit increase in x.
Surefire cure for a hangover, Harry. You take a glass of nearly frozen, unstrained tomato juice, you plop a couple of oysters in there, you drink it down. Breathe deeply. Next, you take a mound, and I mean a mound of sweetbreads. Saute them with some chestnuts and some Canadian bacon. Finally, biscuits. Big biscuits, smothered in gravy. Now, here's where it gets tricky. You're gonna need some anchovies. That should do it.
We keep computing the derivative for all of these different functions using the limit definition. And by that I mean this definition right here. It's the limit of the slope of the secant lines, hence the slope of the tangent line. It's the limit of the average rates of change, hence it's the instantaneous rate of change. And that's great conceptually, but as you've seen, it takes a long time to compute these limits. Is there a faster way? So let's just first observe a pattern that we've seen in some of the examples. So I'm going to write down for you some functions and their derivatives that we've computed. So if we have just the function x, the derivative is 1. Okay. If we have x squared, we've computed that one, and we found that the derivative is 2x. We've also computed the derivative of x cubed, and we found that the derivative was 3x squared. If you plug x to the 4th into the definition of the derivative in terms of a limit, you'll get 4x cubed. Do you see the pattern yet? If you do x to the 5th, you'll get 5x to the 4th. So check it out. There's numbers here. The constants are increasing by 1. 1, 2, 3, 4, 5. And then the exponents and the x are also increasing by 1, but they're 1 less than the constant out front. So here's one way to say what the general pattern is. The derivative of x to the n, where n is a positive integer, is n times x to the n minus 1. Okay, so we've computed a lot of these by hand, and I want to now allow us, in the cases where we do have knowledge, to just apply this computational tool that we've already used. I want us to be able to use this pattern on the fly just to save time. So here are some other observations that we've seen. The derivative of a constant function that's always equal to 0. That's because if your function's constant, then there is no rate of change. It's not changing at all. The rate of change is 0. So for example, if your function is some number like 47, regardless of the input x, then the derivative is going to be 0. Okay? And now there's one other key fact that we need to really start going to town, which is that the derivative is what's called linear. The derivative operator is linear. And that's some highfalutin mathematical statement. What exactly does that mean? What I'm trying to say is that the derivative of a sum of two functions is just the sum of the derivatives. For example, if you look at, let's say, x cubed plus x, then that would be like the f of x function. The x would be like the g of x function. Then the derivative of that is formed by just taking the derivative of the first function. We've seen that that's 3x squared. And then adding on 1, the derivative of the second function, g of x. Alright, now, it's useful to have some new notation for the derivative. And here's how this works. Let's go back up here to our definition. We can think of this limit. The h is like the change in x. So we can think of this as like a delta y over delta x. That's the average rate of change. That's the slope of the secant line. The average rate of change. And now, just as notation, we allow ourselves to write that as dy over dx. The idea here is that as the interval over which you're measuring the average rate of change gets infinitely small, infinitely short, that delta, that's the Greek letter delta standing for change, it becomes just the Roman letter d. So it's supposed to remind us of the delta y over delta x. So this allows us all sorts of new notation. Here's the key, d over dx. If you see that, d over dx of something just means take the derivative of that thing with respect to x. That's the key thing to remember with this notation. So, for example, if we did d over dx of x cubed plus x, that would just mean take the derivative of the whole thing, and we can split that apart as the derivative of the first piece plus the derivative of the second piece. So there's that 3x squared plus 1 again. You can also use this using the y notation. So if y is equal to something like x to the 7th plus 4, then dy over dx is going to be, that's just the notation for the derivative, it'll be the derivative of the first piece. So let's follow our rule to take the derivative of x to the 7th. We take the 7 down and then lower the exponent by 1. That's that rule that the derivative of x to the n is n times x to the n minus 1. I'm using exactly this rule here. It means take the n down and subtract 1. Here I'm doing that for the case of x to the 7. On the other hand, a derivative of a constant is 0. So in this case, the derivative would be just 7x to the 6th. Alright, and now there's one more rule that we need here, which is that the derivative respects constants. Okay, so if a is a constant, it's just some number, then the derivative of that constant a times any function will just be a times the derivative of that function. Or in the more usual notation, a times f prime of x. Okay, in fact, let's form these into a list. These are the basic rules for the derivative. This will actually get you through most simple calculations involving derivatives if your functions are simple enough, if they're polynomial functions. So the first is that the derivative respects constants in the sense that constants pull through. The second is that the derivative respects sums. So d by dx of one function plus another is the derivative of the first plus the derivative of the second. So in other words, that's f prime of x plus g prime of x. And finally is this power rule, this pattern that we've observed, that the derivative of x to the n is n times x to the n minus 1. So we can compute lots of derivatives of polynomials really fast using these basic rules. Derivatives of polynomials are easy. I want to emphasize that. They are easy using these three basic rules. So let's just quickly compute some examples. Here's a classic sort of polynomial. You might have 2x to the fourth plus 3x minus 1. What do I mean by a polynomial? I just mean that it's got powers of x, and those are multiplied by constants maybe, and then added up. So the derivative of this function, we can compute it by just taking the derivative of each piece one at a time and then adding them up. And then since the derivative respects constants, the constants move right through the derivative operator, we can then just take the derivative of each power of x on its own. So check it out. Here the 2 is going to go on the outside. We're going to take the derivative of x to the fourth, and the rule is you bring the 4 down and then subtract 1 to get x cubed. So the derivative of that first piece is 2 times 4x cubed. Next we have the 3, the constant, and then the derivative of x is just 1. So we get that. And finally the minus 1, that's just adding on the constant minus 1. The derivative of that piece will be 0. So altogether, the derivative of this function is 8x cubed plus 3. Not bad. So let's just practice a few more times with some polynomials. Suppose that we have 1/7 x to the 6th minus 2x squared plus x. That's another polynomial. And now we can compute its derivative pretty quickly, just taking each piece one at a time. Let's bring that 6 down. So we get 6/7, and we subtract 1 to get x to the 5th. That's the derivative of this first piece. Next we move along and we bring the 2 down, so that we have minus 4x. Notice that the 2 came down and multiplied by the 2 to give 4, and then I subtracted 1 from the exponent. So that x to the 2 became an x to the 1, that's just x. And the derivative of x is just 1. Alright, next example. Suppose that h of x is x to the 100 minus 52 x to the 3rd minus 17x plus 2. Oh my, that's a complicated polynomial. Imagine trying to write down the definition of the derivative in terms of a limit for that monstrous function. You'd have to think about x plus h to the 100th power. The algebra would be a mess. But because of these three basic rules, we can just
look at each piece one at a time and follow the pattern. So we bring the 100 down as a constant, and then we multiply by x to the 1 power smaller, x to the 99. Next, we're going to bring the 3 down and multiply by 52. Now, don't try this at home. I'm going to try to multiply 52 by 3 in my head. It's 156. You can try that at home. I'm just kidding you, but be careful with that arithmetic there. The derivative of minus 17x is just minus 17. It's just that constant, because the derivative of x is 1, but it's being multiplied by that minus 17. And the derivative of 2 is just 0. I'm not even going to write it.